in this lesson, we begin discussing area and estimating with finite sums. So here's the idea. In this lesson, we begin to develop a method called integration to calculate the areas of general shapes, like the area underneath the curve of the graph of a function. The definite integral is the key tool in calculus for defining and calculating areas. The idea is to approximate the quantity by dividing it into many small pieces, each of which we can approximate by something simple such as a rectangle. Summing the contributions of each of the simple pieces gives us an approximation to the original quantity. As we divide the region into more and more pieces, the approximation given by the sum of the pieces will generally improve, converging to the quantity we are measuring. We take a limit as the number of terms increases to infinity, and when the limit exists, the result is a definite integral. So let's begin by finding the area under a graph. Consider the following. Suppose we want to find the area of this shaded region I've called R that lies above the x-axis, below the graph of y equals 1 minus x squared. This is the graph of 1 minus x squared, and between the vertical lines x equal to 0 and x equal to 1. Now, unfortunately, there's no formula, there's no simple formula for calculating the area of this shape that's bounded by a curve. So one idea is to draw rectangles that contain this region. And we know how to calculate the area of a rectangle. It's just the height times the base, or the length times the width. And so what we're going to do is we're going to draw rectangles. Now, I'm going to clean up our picture a little bit here so that I can show you the rectangles I'm drawing. Consider the following. Here, so what I've shown is two rectangles that together they contain the region R. Now, this is important. Each rectangle has width 1/2. Each rectangle has width 1/2, and each one of them has height. This rectangle here has height 1 unit, and the height of this rectangle is 3/4. Okay, notice that the height of each of these rectangles is the maximum value of the function in each subinterval. So in this subinterval here from 0 to 1/2, the maximum value of the function in this interval is 1. So that's going to be the height of this rectangle. Now, in this subinterval between 1/2 and 1, the maximum value is located here at 1/2, and the maximum value is 3/4. So 3/4 is the height of this rectangle. So because this function is a decreasing function from 0 to 1, that means that the height of each rectangle is the value at the left endpoint of each subinterval. Right? So like on this subinterval here, 0 to 1/2, the left endpoint is 0. And that's going to give me the height of my rectangle. Look at this interval, this subinterval, 1/2 to 1. 1/2 is my left endpoint, and that's giving me the height of our rectangle. All right, so now let's calculate the area of the region. Now this is just going to be an approximation. I mean, I think it's clear in this picture that if I take the value or the area of this rectangle and add it to the area of this rectangle, it will not be an exact value, an exact answer for the area of this region, right? Actually, it'll be we call it an upper sum. All right, because it's actually going to be an approximation that's actually larger than the true area, right? Why? Because all of region R is contained within these rectangles. So just know that our approximation is going to be a little bit too big. All right, so let's do it. So we can say that the area of this region is approximately, okay? So what we're going to do is sum the area of the two rectangles, but as we said, it won't be exact. It'll be an approximation. So it'll be 1 times 1/2 plus 3/4 times 1/2. Remember that the formula for the area of a rectangle is length times width or base times height. And so this is the height of the first rectangle times its the base or the width if you want, plus, and then this is the area of the second rectangle. This is the height of the rectangle, and then this is the base. All right, so this gives us approximately 0.875. Now we know that this is really more than the area of the region. Okay, so what we can do is we can be more precise by, instead of doing 2 rectangles, what if we did 4 rectangles? So let's consider doing 4 rectangles. So here we have 4 rectangles. Now notice that the base of each of these rectangles is 1/4. So these are thinner rectangles. This is going to improve our estimate because we're using thinner rectangles, and it's gonna, together all 4 rectangles still contain the region R. So it'll still be an upper sum. It'll still be an approximation that is a little bit greater than the actual area of the region, but this estimate is going to be better than the previous. Now notice that the height of each of these rectangles, so the height here is 1, and the height is the function value at the left endpoint of this subinterval. The height of this rectangle is 5/16, and we found 5/16 by taking or evaluating our function at the left endpoint of this subinterval. So if this is 1/2, this is the left endpoint here is 1/4. So f of 1/4, or plugging 1/4 into our function, 1 minus 1/4 squared will give us 5/16, which is the height of this rectangle. The point I think I'm trying to make is that the height of these rectangles is found by evaluating the function at the left endpoint of each subinterval. See, for this subinterval here, the left endpoint is 1/2. So the height of this rectangle here is found by evaluating our function, 1 minus x squared, at the left endpoint 1/2, which is giving us 3/4. And the same thing here. This subinterval, the left endpoint is 3/4. So our function evaluated at 3/4 is 7/16. So here we go. The area is approximately equal to 1 times 1/4 plus 5/16. You know what? I think 5/16 is wrong. Let me check that really quick, folks. So 1/4 squared is 1/16. Yes, this should be 15/16. Can we all change that in our notes? So this should be 15/16. All right, cool. That's an easy fix. Okay, so the area of the second rectangle is 1/4 times 15/16 plus the area of the third rectangle is 1/2. Oh, sorry, 1/4. The height. The height is 3/4 times 1/4, which is the base, plus the area of the last rectangle is 7/16 times 1/4. So for each one of these folks, this is the height of the rectangle times the base. The height times I think I messed that up. So this is the height times the base, the height times the base, the height times the base. I guess these should be turned around, but Thankfully, multiplication is commutative, right? The order in which we multiply doesn't change our product. But this is the height times the base. All right, cool. So when you do all of this arithmetic, we're getting that the area is approximately 0.78125. Now this is closer to the actual area of our region R, closer than what we did before. Now, what we could do, each of these are called an upper sum. So I can type that in for us. So this is called an upper sum. The previous one was also called an upper sum. They're called an upper sum because this area, this sum, is obtained by taking the height of the rectangles corresponding to the maximum value of our function. See, for this subinterval here, the maximum value is right here at the left endpoint. The maximum value of this interval is going to be here at this left endpoint. And so each of these rectangles are constructed so that the height of each of these rectangles corresponds to the function value at the left endpoint of each of our subintervals. That's why it's called an upper sum. What we can do is we can instead use 4 rectangles contained inside the region R. I would like to show you that now. So notice here we have 4 rectangles, although the last one has area that's equal to 0, but we have 4 rectangles technically contained inside the region R. Okay, so each rectangle has width, or the base is 1/4, just like before. But the rectangles are shorter and they lie entirely beneath the graph. Entirely beneath the graph. Now the function is decreasing like we said before, right? It's decreasing on this interval from 0 to 1. And so the height of each of these rectangles is given by the value of our function at the right endpoint of the subinterval that's forming its base. So look at this subinterval. It's from 0 to 1/4. The height of this rectangle is found by evaluating our function at the right endpoint, which gives us 5/16, the height of this rectangle. This rectangle, if we take the right endpoint, which is 1/2, and evaluate our function at 1/2, it gives us 3/4, which is the height of this rectangle. The height of this rectangle is 7/16, found by evaluating our function at the right endpoint, which is 3/4. For this rectangle, the right endpoint is 1. And if you evaluate our function at 1, you get 0. And so the height of this rectangle is 0. All right, so let's see. This is going to give us the area is approximately 15. Did I do it again, folks? I did it again, huh? This is supposed to be 15/16. I don't know why I keep wanting to write 5/16. Okay, can you change your notes again? Can you make sure this is 15/16? Okay, if you plug 1/4 into our function, you get 15/16 as a result. I don't know why. I apologize. I don't know why I'm making that mistake over and over again. All right, here we go. At least I caught the mistake earlier this time. Okay, so the area is 15/16, that's the height of the first rectangle, times the width, which is 1/4. The width of all of these rectangles is the same, which is 1/4. The height of the second rectangle is 3/4 times the width, which is 1/4. Plus 7/16 is the height of the third rectangle times the width, which is 1/4. Plus 0 is the height of the last rectangle, the fourth rectangle, times 1/4. If you do all this arithmetic, then you get that the area of the region is approximately 0.53125. Okay, so notice that this area here is less than the area we found before. So when we did an upper sum, we found that the upper sum was 0.78125. And now we're getting 0.53125. Now, I hope it's clear to you that this area here is less than the actual area of the region R. I mean, look at these pieces that we're missing, folks. These small areas we're missing. So this area, this quantity is less than the actual area of the region R. And this was an upper sum. It was more than the actual area. So we know that the area, the true area, is between these two, right? So we know the true, if I can squeeze it, the true area is between these two quantities. Okay. Now, so I've shown you that the more rectangles we're using, the better our approximation. Now, we have used 4 rectangles. For the upper sum, the rectangles were constructed so that the height of the rectangles were the value of our function at the left endpoint of each of the subintervals. This area here, 0.53125, this area was found by constructing rectangles whose heights were the value of our function at the right endpoints. Okay. So what I want to talk to you now about is there's something called a midpoint sum. A midpoint sum, I think our book calls it the midpoint rule, where the height of our triangles, rectangles, will be at the midpoint of each of our subintervals. Let me see if I can show you that now. So here's the method of using what's called the midpoint rule. The midpoint rule for approximating the area. Notice that it's still 4 rectangles, but this is the idea. The height of the rectangles are the values of our function at the midpoints of the bases of the rectangles. So for example, the width of this rectangle is 1/4, just like they've been for the last few examples, but the midpoint between 0 and 1/4 is 1/8. And so I evaluate my function at 1/8, and that's what I make my the height of the rectangle. 63/64 is the height of this rectangle. It is my function evaluated at the midpoint of this subinterval. The midpoint between 1/4 and 1/2 is 3/8, and my function evaluated at 3/8 is 55/64. So this is the height of this rectangle. The midpoint between 1/2 and 3/4 is 5/8, and if I evaluate my function at 5/8, I get 39/64, and that's the height of this rectangle. Finally, the midpoint between 3/4 and 1 is 7/8, and the function evaluated at 7/8 is 15/64. So this midpoint rule gives us an estimate that is between that lower sum and upper sum that I was showing you a little while ago. This is going to give us an estimate that's between those two values. It's not really clear whether this midpoint rule gives us an overestimate or an underestimate of the true area, because you can see this much right here is above our function, but then right here is a little region that's beneath our function. Again, over here, you have a portion that is above the graph, and then here you have a portion that is beneath the graph. So these kind of, in a way, they kind of, balance each other out, if you will. So we're not really sure whether at this point, at least, we're not sure whether this area that we're about to write down is an overestimation or an underestimation. All right, we're ready to write down the area. So the area is approximately equal to the height of the first rectangle, 63/64, times the width, which is the base, which is 1/4. Okay, plus the height of the second rectangle, which is 55/64, times the width of that rectangle. Now the widths are all the same, so I could just keep on writing 1/4, right? And then the height of the second rectangle is 39/64 times the width which is 1/4. Finally, plus the height of the last rectangle, which is 15/64 times 1/4. If you do all of this arithmetic, you'll get that the area is approximately 0.671875. So here's a little summary of what we did. The first thing we did is we found this upper sum, and what we did was we drew 4 rectangles, each whose width was 1/4. What's really important is that the heights of the rectangles were the function evaluated at the maximum value of each subinterval, which happened to be the left endpoints of each subinterval. And then we found a lower sum, and the heights of these rectangles were the function evaluated at the minimum value of each subinterval, which happened to be the right endpoints. And then finally, a more accurate, but still an approximation, area of our region was using the midpoint rule. I'm calling it a midpoint sum. And this is where the heights of the rectangles are the function evaluated at the midpoint of each subinterval. Now, notice that for each of these different sums that we found that approximated the area of our region, the interval a to b, in our example, it was from 0 to 1. But in either case, that closed interval was subdivided into subintervals. Now, we had 4 subintervals. We had 4 rectangles. But in general, we have n subintervals. And what's important is that they have equal width. Each of the rectangles have equal width. And the width we can write as delta x, the change in x, and it is b minus a, the right endpoint minus the left endpoint, divided by n. So in our example of the rectangles we just drew, our interval was from 0 to 1, so this would be 1 minus 0, which is 1, divided by, we chose to draw 4 rectangles. Of course, we can draw more rectangles if we wish, and so that would be 4. So 1 minus 0 over 4 is 1/4, and 1/4 was the width of each of our rectangles. Now, furthermore, the function was evaluated at a point from each subinterval. Now, we can call this point from each subinterval at which the function was evaluated C sub k. C sub k is the point at which the function was evaluated, and we found the height. That value determined the height of each of our rectangles. Now, C sub k for let me see if I can move this screen back up here. There we go. For this upper sum, that C sub k would be the left endpoint. For the lower sum, I know this is kind of messy. See if I can move this around. Okay, for the lower sum, that C sub k would be the right endpoint of each subinterval. And for the midpoint sum, C sub k would be the midpoint of each subinterval. Okay, so we are, if I can get this screen to move. All right. So this C sub k is a point from each subinterval at which we're evaluating our function, and it gives us the height of the rectangle. So in each case, the finite sum has the following form. It will be f at c sub 1 times delta x plus f of c sub 2 delta x plus f of c sub 3 delta x, and etc., plus f of c sub n delta x, where each of these c sub n's, these are the points at which the function is evaluated from each subinterval. Okay, so this is giving us the height f of c sub 1, f of c sub 2, f of c sub 3, f of c sub n. All of these are the heights, and each of these delta x is the width of each rectangle. So when we are adding all of these terms, we're basically adding the area of each of these rectangles. Now, the idea here is that we're going to make more rectangles, right? By taking more and more rectangles with each rectangle thinner than before, it appears that these finite sums give better and better approximations to the true area of the region R. So what I want to do is I want to give you some like a little summary of what the sum would be if we drew 16 rectangles, 50 rectangles, 100 rectangles, 1,000 rectangles. What would these sums be? Just to give you an idea of what's happening to our approximation. So check this out. So all the way from 2 rectangles to 4 rectangles, and this is what we did earlier. But if you go up to 16 rectangles, notice how it seems to me like, you know, look at 1,000 rectangles. Look at this midpoint sum. It seems like these approximations are approaching the number 2/3, right? This decimal is practically 2/3. In future lessons, we will be taking a limit. Okay, we will be taking the limit as the base width of each rectangle goes to 0. In other words, we're making these rectangles super, super thin, and we're going to let the number of rectangles go to infinity. And we're going to show that the area of our region R is actually exactly 2/3. So keep an eye out for that. Once we continue to dig deeper into this idea of using finite sums, we're going to eventually be able to show that the area is exactly 2/3.